an associate professor at the University of Illinois, and he'll be telling us about driving nitride-micro-LEDs with thin-film transistors built on solution processable copper indium selenide compound semiconductors. So yeah, thank you. Whenever you're ready, please do start. And I'm really curious because I did my PhD on TFT, so I'm looking forward to your talk. Yeah, good luck.
Okay, excellent. So you guys can hear me okay, right?
Yeah, everything's fine. We can see you. We can hear you very well.
Okay, great. Yeah, thank you for the introduction. So it's a great pleasure to be here. So I will take this opportunity to talk about our recent works on driving those nitride-based micro LEDs with thin film transistors, specifically those built on the solution processable copper indium selenide order defect compound semiconductors. So we do not need to overemphasize in this particular symposium, like why we believe micro LED represents the future of display technologies, right? So in micro LED displays, we have the light generated directly from each gallium nitride-based LED pixels with size on the order of a few microns, and compared to liquid crystal displays or organic light emitting diodes, those inorganic micro LED display offer much higher energy efficiency, higher achievable brightness and contrast, longer lifetime, and also potentially better color performance. Okay, so associated with these good properties, one challenge we have is how we're going to be able to drive these ultra bright pixels in an active matrix display using the selector transistors, especially for high resolution displays where the footprint of each pixel is going to be very limited. While compared to LCD and OLED displays, the much higher current flowing through the inorganic micro LED makes it almost impossible, right, to drive them using thin film transistors built on conventional materials like amorphous silicon or even semiconductor metal oxide. Well, instead, people typically going to have to use single crystal silicon transistors, or the so-called silicon CMOS backbone. Advanced materials like 2D materials has also been utilized, but in both cases, the size achievable is greatly limited by the size of the silicon wafer we have as our starting substrate, which is up to 300 millimeter in diameter. Right. On the other hand, right, for commercial applications, if you look at our competitors, those micro LED displays needs to be driven by transistors built on a semiconductor that can not only offer the high performance, but also can be formed with low cost over large area, right? Especially if we want to be competitive against those very large size LCD displays. And for this large area electronics, it is highly desirable if the semiconductor material itself can be deposited from solution with high throughput, low capital cost, and also excellent scalability using techniques, for example, slit casting as an example. Right. So people have been exploring solution processable semiconductors for many years, right? So here I list some candidates that have been tested before, including polysilicon formed from silent precursors, the colloidal quantum dots, metal oxides, perovskite, and also binary metal collagenide, including various nanomaterials, including carbon nanotubes, so 2D semiconductors, as well as different type of organic semiconductors. But the problem is they all share a common challenge for us, right? Especially within the framework of application together with the inorganic micro LEDs. While those solution processable semiconductors, they typically have a relatively low performance as limited by the high density of structure imperfections created in this low temperature solution deposition process. And this is basically limited by kinetics and entropy terms in thermodynamics. So in certain sense, it's kind of like a fundamental material science problem. So then the question we have here is, well, can we find a solution processable semiconductor material that can demonstrate high performance while at the same time tolerating those detrimental impacts from those material defects? Right. So one particular class of material turns out to be very promising for this purpose, and this is what we call the order defect compound semiconductor.